So I'm going to review some of the things we talked about similar triangles and those geometric mean theorems. We discussed how when an altitude is drawn in a right triangle from the vertex, which is the right angle, to the hypotenuse of the opposite side, that you've got three similar triangles that are created. You've got a big triangle, you have a medium triangle, and you have a small triangle. And when you sketch these, you're going to need to line up the long legs in the same way and the short legs in the same way so that you can identify corresponding parts. Now this will sometimes be hard, sometimes it'll be very obvious, and our geometric mean theorems come in handy if we have a hard time figuring out which is the longest leg, which is the shortest leg. So the geometric mean theorems, we had one that dealt with the altitude that we draw that creates the three different triangles, and we have two that deal with each of the legs on our original triangle. When we draw the altitude to the hypotenuse, then it divides that hypotenuse into two different segments. And what we find is that the altitude is then the geometric mean of each of those two segments. So if I have this triangle drawn, and ACB is my original, line CD is my altitude, then I can create this proportion to solve for missing pieces, knowing that line CD, which is my altitude, is the geometric mean of each of the two pieces that are created when the altitude runs into the hypotenuse. So what that means is CD is the geometric mean. It goes twice in my proportion across from each other of this piece and this piece. So once I figure out which one is the geometric mean, AD can go here, DB could go here, or they could be flip-flopped as long as you're across from each other and they end up multiplying. Now our leg theorems are similar. You just have to figure out what pieces are going to be the geometric means. So just like the altitude could be a geometric mean, each of the legs on my original right triangle can be the geometric means. So AC is one of my legs on the triangle. It is going to be the geometric mean. In other words, AC goes diagonally in my proportion of the whole hypotenuse in the part of the hypotenuse that's adjacent, or you want to think about closest to leg AC, okay, which is going to be AD. So again, I have AC diagonal across from each other. That's the piece that's the geometric mean. AB and AD can go in either one of these spots. You can flip them around as long as they're going to multiply together. So then I can go look at the other leg, leg CB, and that is going to be the geometric mean of the whole hypotenuse again in the segment of the hypotenuse that is adjacent to leg CB, which would be DB. Now we also reviewed that we could sketch each of these triangles, and that is totally fine if you want to do that. Let me show you how this relates. So if I have the original triangle and I create this large triangle, medium triangle, small triangle, I line up the long legs up here, the short legs down here, then I can compare long leg to long leg, short leg to short leg. Okay, so if I look at AD to CD, where are AD and CD in the same spot? Here and here. So I'm comparing medium triangle to small triangle. CD is the short leg on the medium triangle. Oops. Okay, here we go. So CD is the short leg on the medium triangle, and DB is the short leg on the small triangle. If I were to set this up using my geometric mean altitude theorem, this is the altitude, and it's the geometric mean of this piece and this piece. You get the same answer. So there's two different ways you can get this information. It really just depends on which way you like to use best, but they will all get you your missing pieces of information.